In this lecture, we're going to first look at other types of bonding, in particular pi bonds, I guess. It's just the only other type of covalent bond we're going to look at in this class. We're going to look briefly at pi bonds, and then we're going to move into how orbital hybridization and molecular geometry are affected by pi bonds. So let's get into it. Now, sort of a strange question to ask at this point, it seems, but a question I like to ask nonetheless is, how many pi bonds are in hydrogen cyanide? Well, let's do how many total bonds. Total sigma and pi bonds, that is. Are in HCN. Okay, and I've drawn the Kekulé structure out for us. So it looks like we've got 4 bonds total. Okay, how many of them are sigma bonds? And how many of them are pi bonds? So, a few things to note. All single bonds are sigma bonds. Some like alliteration to it or something, I like it. Anyway, all single bonds are sigma bonds, and any 2 atoms can be connected by only 1 sigma bond. You can only have 1 sigma bond These are 2 important points. You can only have 1 sigma bond between any 2 atoms that are connected or covalently bonded. So I know that 2 of these atoms are connected by triple bonds, but we can only have 1 sigma bond in there. So a few ways to look at this. I'm going to kind of, let's zoom in on this. I could, okay, I can't make that like that much smaller. There we go. So that is a sigma bond, and this is a sigma bond. So our sigma bonds are the bonds highlighted in yellow. And it could have been any one of the 3 bonds between the carbon and the nitrogen. I'm just showing you the top one, or the middle one, excuse me. So with that in mind, we only have 2 sigma bonds, a sigma bond between hydrogen and carbon, and then a sigma bond between carbon and nitrogen. You can only ever connect 2 atoms together by 1 sigma bond. However, seemingly, if we have 4 bonds total, that means that we have to also have 2 pi bonds in our system. And that's true. So we have 2 pi bonds that are connecting the carbon and nitrogen together. Now what this means is that while any 2 atoms can only have 1 sigma bond, they can have 1 to 2, and really that's kind of it, pi bonds. But atoms can have 1 to 2 pi bonds. Now we're not going to look at the orbital depiction of a pi bond just yet. We'll save that for probably next lecture or something. Anyway, so what this means is that atoms can have an additional 1 to 2 bonds as pi bonds. So a double bond, all double bonds, and let's just have generic element A with boron, I guess. Okay, so we've got 2 bonds. They are bonded together by a double bond. Okay, whatever these 2 elements are. It can't really be boron. It can't form double bonds that easily. Anyway, we have a double bond. A double bond is going to be comprised of 1 sigma bond plus 1 pi bond. Always and forever. Because you can't have more than 1 sigma bond, and you really can't connect 2 atoms without a sigma bond. And we'll see the orbital depiction of that later. But if that's true, then a triple bond, let's pick real elements this time, carbon and nitrogen, cyanide, sure. That's going to always have 1 sigma bond and 2 pi bonds. So our 3 bonds in a triple bond come from 2 pi bonds plus 1 sigma bond. Oop, okay, there we go. Okay, whereas the double bond is 1 sigma bond and 1 pi bond. So you count the total number of bonds you have, 1 for single bond, 2 for double, 3 for triple, and then you're going to have at least 1 sigma bond, plus however many pi bonds you need to get up to 1, which would be 0, 2, which would be 1 additional 1, and then 3, which would be 2 additional bonds. Okay, so how do we get these things aligned? What does an orbital look like in a double bond and a triple bond? So there's something that's kind of awkward and interesting that emerges, and that is when pi bonds are involved. When we have pi bonds involved, not all p orbitals are used in hybridization. So we looked at hybridization last time, and we said, hey, we need to attach to 4 things. So carbon needs to take all 4 of its valence orbitals, the s and the 3 p's, and do rehybridization on them, or hybridization on them, to get to 4 sp3 orbitals. But what if we only need to bond to 2 things or 3 things, not up to 4 things? Then we don't need as many p orbitals. Everybody loves the s orbital, and we're always going to use the s orbital, but we don't need all of those p orbitals. Okay, so let's say, for example, we have HCN. And I ask you the question, what is the hybridization of that central carbon atom? Okay, so here's the trick for determining hybridization. Okay, and the trick is the number of things on an atom. The number of things on an atom is equal to the number of atomic orbitals used in hybridization. Okay, so that's my little trick. It works well if you know how to count things. Okay, so things was this word that described lone pairs, and lone pairs count as 1, and atoms. Okay, so what's the hybridization on H, C triple bond N if we're looking at the carbon atom? Well, how many things does it have? It has 4 bonds, yes, but we're not counting bonds as a thing. We're counting lone pairs, and we're counting atoms. So how many things are attached? Well, 1 from hydrogen and 2 from nitrogen, so we have 2 things. Okay, so if we have 2 things, that needs to equal the number of atomic orbitals. And the atomic orbitals that we use are always the valence orbitals. So that's going to be the 2s, the 2px, the 2py, and the 2pz. These are the 4 orbitals that we can use in hybridization. Now, what I said was we're going to use the number of things are going to equal the number of orbitals that we use. So we have 2 things, we only need 2 orbitals. That's going to be the 2s, and then just because it's close for highlighting purposes, the 2px. It could have been any of them, but it's only one of the p orbitals in addition to the s. We always use the s. If we can get away with it and we don't need them, we're not going to use all of the p's. So the hybridization is going to result from mixing one of the s orbitals and one of the p orbitals, mixing the 2s and one of the 2 p orbitals together. And to get out, what we'll get out is, from hybridization, we'll get 2 times some hybrid orbitals. Now, what type of orbitals are they? Well, how do we name them? We name them based on the orbitals that go in. So we used an s orbital and we used a p orbital. In the past, we'd use 3 of the p orbitals, so we'd call them sp3. Here, we're only using 1 of the p orbitals, so we call it sp. Again, chemists don't like the number 1 for some reason. Okay, so sp hybrid orbitals are formed. Okay, so the py and the pz were not used in the hybridization process. So what happened with the py, and I'll put 2 in front of it, and 2pz orbitals? Well, they weren't used in hybridization. Okay, that's important to know. They weren't used in hybridization, and instead they were used to make pi bonds. And we'll look at the orbitals of pi bonds in the next lecture. But for now, let's kind of stick with hybridization and the impact that pi bonds have on hybridization. Okay, so let's look at formaldehyde, kind of a nasty chemical, but an interesting molecule in terms of studying molecular geometry. And let's focus on this carbon atom. So what is the hybridization of the carbon atom? Hybridization is equal to the number of things attached. And really, that equals the number of orbitals. So the number of orbitals that we need out of 2s, 2px, 2py, and 2pz that we need for the central carbon atom in formaldehyde is equal to the number of things attached to that carbon atom. So how many things are attached to the central carbon atom? We have 1 at H, 2 at H, and 3 at O. So we have 3 things. So how many orbitals do we need? We have the 2s, the 2px, the 2py, and the 2pz. The 2s is always used. And then this time, we need to hit 3 orbitals. We're not going to use all of the p orbitals. We'll use 2, because 2 plus 1 equals 3. It's going to leave the 2pz orbital out in the dust, right? No, it's going to be involved in forming a pi bond. And if you see, we have 1 pi bond being formed between the carbon and oxygen. That's what that 2pz orbital is going to be used for. But in terms of the hybrid orbitals that we're actually going to be using for sigma bonding, those are going to come from the 2s, the 2px, the 2py, and the 2pz, and they're going to mix together in our hybridization event. As the hydrogens and oxygen come close to the carbon for bonding, they're going to mix in a hybridization event to make 3, because we put 3 orbitals in, we get 3 orbitals out. And these are going to be s, p. How many p orbitals did we use? Not 1, not 3, but 2. So we have 3 sp2 orbitals. Okay. So let's go back and continue our discussion of geometry. Molecular geometry. And we had some players, right? We had the tetrahedron. We had what? Pyramidal. And we had bent so far, but those weren't the only players. We also have to consider the other 2 I had on the list, which are trigonal planar, which is 4, and 5 is linear. Okay, so these first 3 we've already touched on, and these first 3 have a tetrahedral arrangement. That is, we've got 4 things attached. 4 things attached. So all of these in this above case are, see if this will work, sp3. All of these use sp3 hybrid orbitals. I don't like that 3, sorry. All of these use sp3 hybrid orbitals. So the first 3 of these use sp3 hybrid orbitals. They all have this tetrahedral arrangement. Now the other 2 are kind of interesting examples. The trigonal planar, this has sp2 hybrid orbitals. sp2 hybrid orbitals, whereas the linear arrangement has sp hybrid orbitals. So linear, sp, trigonal planar, sp2. Now let's look at this. Formaldehyde shown as having a carbon atom, a central carbon atom that we said was sp2. That central carbon atom is sp2. It only has 3 things attached to it. Look at the 3 things. Based on how this is drawn, could I draw this any better in terms of spreading things out? Okay, if I don't think so. That is to say, I don't need any wedges or dashes on this formaldehyde structure, because putting a hydrogen out of the piece of paper or into the piece of paper doesn't do any good. Everything is spread out as much as possible, right? If I've got these 2 things split out this way and then 2 things, my double bond pointing straight up, they're spread out as much as possible. They're spread out 120 degrees. That's as good as it gets in a case like this. There's no reason to add any wedges and dashes, which means there's nothing coming out at you or going away from you. There's no 3D component. This is perfectly flat. No wedges or dashes. Now, similarly with a linear structure, now linear was what we used to describe the central carbon atom in hydrogen cyanide, HCN. Okay, it's linear. If you look at it, it looks like a straight line, right? We've mentioned this. Straight line, it's linear. Why does that matter? Well, it matters because now we have 3 points to make a straight line. That's not given. If you have 2 points like dihydrogen, that's not linear. Anything where you're connecting 2 atoms together and only 2 atoms, that's not a linear geometry. It just has to be a straight line. But when 3 points make a line, that's an interesting observation. Now y equals mx plus b across those 3 points. Okay, so what we've done here is we've taken our 2 things and we've provided a maximum separation, not of 109.5, not of 120 degrees for that bond angle, but now at 180 degree bond separation. So when we have 2 things attached to our central carbon atom, we can do maximum separation if they're 180 degrees apart and they form a straight line. So anytime you've got a central atom, or you've got the atom that you're looking at is sp hybridized and it has atoms on either side of it, it's going to be linear. Anytime our central atom has 3 atoms attached to it and only three things, and all those things are only atoms, we're going to see a trigonal planar geometry. Okay, so let's look at other examples of this to try to bring this into some context here. What if we have carbon dioxide? What is the arrangement? Well, let's get away from that word here. What is the hybridization and geometry of each atom? Okay, so what is the hybridization and geometry of each atom in carbon dioxide? Well, what we're going to do is for each atom, we're going to count the things. The oxygen atoms are the same in either case. They have 2 lone pairs plus 1 atom. That's going to be 3 things. So if we have 3 things around that oxygen atom, we're going to need 3 atomic orbitals to get us to our hybrid state. Well, I just goofed that up. sp3, no thanks. I need an s plus a p plus a p. That gets me to 3 orbitals total. It gets a little confusing because the s orbital counts first. So it's not sp3, because that would be 4 orbitals. It's sp2 from an s and 2 p's. Okay, what about the central carbon atom? Now again, that applied, what that analysis I just did on the left-hand oxygen applies to the right-hand oxygen as well. So let's go ahead and look at the carbon atom. So we have 2 atoms, 0 lone pairs, That's going to give us two things. Two things mean we need an S plus a P. Okay, so we add those together, we get the sp hybrid orbitals. Now, what about geometry? Okay, let's start with the sp orbital situation. So carbon has 0 lone pairs and is sp hybridized. Well, that then turns out to be linear. And if you look, linear, we form a straight line where the thing that's actually forming the line is the carbon atom. It's not the oxygen atoms. Okay, so what about the geometry of the oxygen atoms? So the geometry, I'm going to do this. Okay, so the geometry for the oxygen atoms, they both look like this. If you look, everything's arranged flat on a flat surface. We said that oxygen was sp2 hybridized. It has a trigonal planar arrangement of its three things. Because anytime you've got three things, it's going to be a trigonal planar arrangement. Anytime you have two, it's going to be linear. Anytime you have four, it's going to be tetrahedral. That's not going to change. But what does change is that when you have lone pairs of electrons, you can't see the lone pairs. They're like ghosts or something. That's terrible. I'll just do this. Okay, I can't see the lone pairs of electrons. All that I can see is the oxygen bonded to the carbon atom. We need two things attached to the atom of interest to make a geometry. Two things, and or more. So 2, 3, 4, we have a geometry. 1, no geometry. So the answer here is, even though we have a trigonal planar arrangement, because we can't see everything, we have no geometry. So when you introduce lone pairs of electrons, you start to take away some of the features that give it its interesting geometry. Now, if we have two atoms attached, all of a sudden we can get to geometry. So let's look at another example. Let's say we've got, okay, let's say we've got this structure. So if we do the analysis, we're going to see that this is sp2 because it's got three things attached to it: hydrogen, hydrogen, nitrogen. Up here, this has two atoms attached to it, and it's sp2. You might be like, wait a second, why is that sp2? It's only got two atoms attached to it. Don't forget your lone pairs of electrons. You got to get to an octet somehow. So sp2 hybridized there, sp2 hybridized there, and then sp3 hybridized here. So let's look at the carbon atoms. This sp2 hybridized carbon atom is trigonal planar. It has a trigonal planar arrangement, and at every site we have atoms. So we don't have to worry about not being able to see pieces of it because we have atoms everywhere. Up here, this is sp3 with no lone pairs of electrons, so we don't have to worry about pyramidal or bent or anything like that. It's just simply tetrahedral geometry. But what about this nitrogen atom here? In this nitrogen atom, now we have lone pairs of electrons, so we've lost part of our trigonal planar system. Now before, we had oxygen atoms that lost everything except the atom it was attached to, which means if you've only got one atom that you're attached to, you can't have a geometry, right? If you look at our hydrogen atoms, they each have no geometry. But that's not the case for our nitrogen here. Our nitrogen, if I zoom in on this, if I zoom in on the nitrogen, what we have is a trigonal planar arrangement of our three things. I'm going to erase the CH3, keep the C around. Trigonal planar around the nitrogen atom. Okay, so everything is flat. Everything is 120 degrees separated. But all that I get, all that I can see is this. We have three things in a line, but that line is not straight. It's not linear. It looks like any other kind of three data points. They form a plane, but they don't form a straight line. Instead, what we have is a trigonal planar arrangement with a bent molecular geometry. Molecular geometry. So this is what kind of happens as you start to introduce lone pairs of electrons. You chop out pieces. You chop out pieces of your atom, and so you start to lose things. Okay, but if you've got at least one atom, if you've got one atom in the center and two atoms on the sides, you can start to define a geometry, for example, as being linear or bent. If you add a third piece, it could be all in the plane, which is trigonal planar, or kind of tilted up, which is pyramidal. If you add that fourth piece and it's an atom, then you're at tetrahedral. Okay, so what we need to be able to do is that in every case, we need to be able to identify the hybridization. And the hybridization tells us the arrangement. sp3 is always tetrahedral. sp2 is always a trigonal planar arrangement. sp is always a linear arrangement, excuse me. But then the geometry is dependent on how many of those things are atoms. So if you have a tetrahedral arrangement and they're all atoms, then it's a tetrahedral geometry. If only three of them are atoms, it's a pyramidal geometry. If two of them are atoms, it's a bent geometry. If one of them is an atom and the other three are lone pairs, it has no geometry because you need at least two atoms to get to a geometry. If you go from trigonal planar arrangement, three atoms, it's trigonal planar. Two atoms is bent. One atom is one atom and it's no geometry. Okay, what if you're at two atoms in an sp arrangement, or an S with sp hybridization, then you're at a linear geometry. Take away one of them to make a lone pair, and you're at one atom and you have no geometry. Okay, so it's a lot to take in, but man, is it important for understanding molecular geometry, not only for molecules right now, but any molecules we look to study going forward, whether that's in organic chemistry, biology, or biochemistry. This is how things get their three-dimensional shape.